Hi everyone. No matter you are from the Zhujiajiu room in the conference venue in Shanghai or somewhere online, good morning, good afternoon, good evening. Welcome all of you to our SIG-by-SIG-DA workshop on the emergent techniques in system design and design automation for embedded system. Hybrid event co-located with ESWeek 2022. My name is Chenren from Peking University. I'm also serving as a cross-SIG activity director for ACM SIGBAT, and this is you see why I'm here to organize this event. And this is our workshop program co-chair, Professor Mingsong Chen.
Hello everyone, my name is Mingsong Chen from
Can you hear us?
Yes, can you hear me?
Yeah, we can hear you.
Yeah, okay. Hello everyone, my name is Mingsong Chen from East China Normal University. I'm also the local arrangement co-chair of ESWeek this year. So, welcome.
Yeah,
okay.
We are super excited to be here with you, and hopefully we will have a wonderful time in the rest of the half day. So we are all here today because we are part of SIGBAT, SIG-DA, or both communities. Today we are observing many active and vibrant trends in this field, primarily because first we have stronger needs and mature technology than ever to interface the physical world with the cyberspace to cultivate new AIoT technology, application, and data. And second, the customization nature of the embedded system makes it relatively easier for tape out is much lower, which really facilitates the EDA to be more closer to the ground. So by realizing these facts, we hope this workshop is a kickoff attempt to bring together the experts and expertise from both academia and the industry to present the latest results in the intersection of embedded system and design automation. And the focus of the workshop is to promote the research idea exchange between these two community and generate new research direction in both community. And the idea of this event is actually proposed by our SIGBAT chair, Professor Steve Liu. Let's welcome Professor Liu to give us an opening remarks.
Hello, everyone. Can you hear me?
Yes.
That's great. Thanks, Chen, for the introduction. Dear distinguished speakers, colleagues, and fellow students, I want first to greet everyone. Good morning, good evening, or good day, depending on where you are right now, attending the ESWeek and specifically this event. So as Chen already mentioned, so my name is Xue Liu, and I'm a professor at McGill University. And also I'm the chair of the ACM SIGBAT, Special Interest Group of Embedded Systems. So it's a great honor and pleasure to have this opportunity today to get together with researchers from ACM SIGBAT and also ACM SIG-DA to attend this first SIGBAT SIG-DA joint workshop on emerging technologies in system design and design automation for embedded systems. So this half-day workshop is one of the activities of Embedded System Week 2022. And of course, you may know ESWeek is one of the two major scientific events which SIGBAT sponsors, and the other one being CPS IoT Week. So this workshop, in fact, is the first activity event of the ACM SIGBAT Cross-SIG Forum Series. And this is started this year. As a focal point with the ACM for all aspects of embedded computing systems and the cyber physical systems. So ACM SIGBAT always strives to serve not only its own community, but also the whole ACM community together. So this Cross-SIG Forum Series is one of the activities we organized to facilitate the idea exchanges and the communications with other fellow ACM6. So this time, SIGBAD associates with SIGDA, thanks to Chenren for the leadership, to start this workshop. As we know, for a long time, embedded systems have been recognized as a key discipline, including new computer and system science foundations, new design technology, and new hardware and software frameworks. Today, as 5G starts to penetrate our daily life, embedded systems has becoming a key driving force, more important than ever. The ACM SIGBAD Cross-SIG Forum Theorems, and in fact, today is the #1, the inaugural workshop, which is the SIGBAD and SIGDA joined together workshop. It's a kickoff attempt to bring together the experts from both academia and industry to present the latest results in the intersection of embedded systems, which SIGBAD focus on, and also design automation, which SIGDA focus on. And the focus of this workshop is to promote the research idea exchanges between these two communities and generate new research directions, which aims to benefit both SIGBAD and SIGDA. The program of this workshop is exciting. We have 4 invited talks and a panel discussion with experts from both communities. The panelists and researchers from both academia and industry. And with this exciting program, I'm sure the workshop will be a very successful event. As I mentioned, the goal is to facilitate the idea exchanges and spark new ideas from different communities. On behalf of SIGBAD, I would like to thank our workshop chairs, Chenren and Mingsong, for their hard work and organization. And also I'd like to thank ACM SIGBAD and SIGDA colleagues for their great support. I also want to thank all the invited speakers, panelists, and also all the attendees here. Last but not least, I want to conclude to wish a full success of this SIGBAD SIGDA workshop and hope we have more upcoming cross-SIG events in the pipeline. Wish all of you enjoy the workshop and have a pleasant gathering. Thank you very much.
Okay, thanks, Steve, for the opening remarks. So this is the rest of the program today. We see I will be chairing the 4 exciting invited talks, and then we'll take a short break, and then Mingsong will chair the panel discussion. And I would also like to thank all the advisory committee member, including Professor Xue Liu, our SIGBAD chair, Professor Jie Liu, our SIGBAD China chair, Professor Yiran Chen, SIGDA chair, and Professor Sharon Hu, she is the past SIGDA chair, and also Professor Qingfeng Zhuge, Karen, for their great and tremendous support in participating in the discussion on how to organize this event, which the topics to discuss. We are very grateful to all their help. Okay, so then now let's welcome the first exciting talk, Qi Zhu. He is the associate professor at the EC department of Northwestern University. He received his PhD in ECS from UC Berkeley and a bachelor degree in computer science from Tsinghua University. His research interests include design automation for CPS and IoT, safe and secure machine learning for CPS, for CPS and IoT, cyber physical security and system on chip design with applications in domains such as connected and autonomous vehicles, energy efficient smart buildings, and robotic system. He is a recipient of NSF Career Award about research fellowship for experienced researchers. He received several best paper awards, including DAC, ICCPS, TODAES, and the DATE. He is also the conference chair of IEEE TCCPS and VP of Young Professionals at IEEE CEDA, and he is also the associate editor for IEEE TCAD, ACM, TCPS, and IET Cyber Physical System theory and applications. Without further ado, let's welcome Professor Qi Zhu to give us a talk on design automation for machine for learning-enabled cyber physical system challenges and opportunities. Okay, let me stop share.
All right. Let me try to share the screen. I think this one. Can you see my screen?
Yeah.
Go to the presentation mode. Okay. Yeah. Thanks, Chenren, for the nice introduction. And sorry that I should have shortened it. And thanks for organizing this wonderful event. I have to apologize a bit. I have been having a quite bad flu, so my my voice may not be very clear. But today I feel I'm glad to share some of our work that we've been doing on learning-enabled cyber physics systems. I will especially talk about it from sort of a design automation perspective, meaning what types of design methods, design methodologies, and design tools that may be useful for these types of systems. Given the time limitation, I'll mostly stay at the higher level. But if you're interested, you're very welcome to follow up, and we can discuss more offline. Excuse me. So between, I think this is a great workshop, the topic. Between embedded systems and the design automation, the two communities have long been, I think, very close. And for design automation community, there has been a long history of trying to develop design methods for embedded systems. I remember when I was a graduate student almost 20 years ago, we were working on some of the sort of emerging embedded systems, like especially like vehicles, smart buildings, etc. So what have been sort of changing over the, I guess, the last 2 decades or so? If you look at more classic embedded systems, we see something like thermostat, right, which you can program to some circumstance. In the early 2000s, we also saw the appearance of those robotic dogs, and back then there were a lot of works on designing vehicle electronics, right, by using various design automation methods, especially that things like timing analysis tools and tools for optimizing the embedded chips. Those are very, I think, familiar to audience in these communities. But over the last 2 decades, I think two things that have really been advancing for embedded systems. One is that a lot of those systems, they have become a lot more closely integrated and being interacting with the physical environment, right? So if we look at now modern vehicles which have autonomous driving functionalities, now instead of relying on the human drivers to sense the environment and make decision and apply actuation control, the autonomous vehicles, the entire cyber path, right? They will be in charge of the sensing of the environment, making intelligent decisions, and make sure everything is safe. Similarly, for robotic systems, right? When we go from the early days of robot dogs to things like what Boston Dynamics has been making. Those newer robots, they are fairly intelligent and they can sense and interact with the environment in a much closer manner. And then the second trend, which really is behind this sort of close interaction with the physical environment, is the adoption of really advanced machine learning techniques, especially the ones that are based on deep neural networks. So we are seeing this trend of moving evolution of the traditional embedded system to what we call learning-enabled cyber-physical systems, where the embedded computing part closely interact with the physical environment based on fairly intelligent learning-based perception, planning, control modules inside. So in terms of design automation methods or design automation tools, right? In the early days of designing embedded systems, challenges we have been trying to address are, for instance, resource limitations, right? Energy efficiency of the systems, timing requirements, which are not only important for performance, but in many cases very critical for system safety. And just in general, right, system safety, reliability, security, those who have always been sort of key challenges that these automation tools trying to address. And I mentioned about some of the works that have been always very active in research community, right? For instance, for vehicle electronic systems, how do we do scheduling? How to make sure the timing requirements are met? Those are very challenging problems, and even up to today, they are still very challenging problems with the evolution of the computing system, both in terms of software and hardware. But then on top of this, right, if we look at those learning-enabled cyber-physics systems, what are some of the new challenges that we have to deal with? First of all, because now we are closely interact with the physical environment, the physical environments, they are quite complex. If we try to capture them, right, with sort of accurate models, those are typically continuous dynamics. If you want to capture them fairly accurately, we are looking at sometimes hundreds or thousands of differential equations or even more. And on top of the complexity, those physical environments are often quite dynamic and uncertain. So this degree of uncertainty is a big challenge in designing such systems, and I will talk more about it in today's talk. And then on the other hand, as I mentioned, there's increasing adoption of neural networks, and those lead to significant challenges in analyzing system safety, robustness, or even security. This is not only because of the complexity, right, of those neural networks themselves, and also because of the sort of added effect of the uncertainty in their input. And then if we think about, right, how do we actually train those neural networks? Often they require significant amount of data and high quality data with relatively accurate labels. Those are often hard to obtain, especially for those learning-enabled cyber-physics systems, different from some of the domains which machine learning have shown success. For instance, right, image recognition, etc. For this type of learning-enabled cyber-physics system, because of the complexity and the uncertainty of the environment, it's often difficult to have a sufficient coverage of all different types of scenario and provide high quality data and data labels for their training. So I'll also talk a little bit about that, how we may address those. So I'll first start with how do we tackle on some of those uncertainty challenges in learning-enabled cyber-physics system, and especially try to ensure system safety. And I'll use connected and autonomous vehicles as an example. And these types of systems, if we think about connected and autonomous vehicle, CAV, the sense the physical environment with fairly advanced perception algorithms, and then based on that, apply prediction, localization, then planning and control. For perception nowadays, it's almost entirely deep neural network based. For planning and control, there's increasing interest of using deep neural network as well, not necessarily deep, but using neural networks as well. Those types of algorithms are being then sort of mapped onto a cyber platform, right, where it will run on fairly advanced software hardware platform nowadays with usage of multi-core CPUs, GPUs, FPGAs in some cases. And then if we look at such systems, the degree of uncertainty and sometimes disturbance from the environment is ubiquitous, all the way from the inherent uncertainty in the input to sensor noise, to the inaccuracy, right, of your perception models. No matter how well, right, you train your perception models, there's a degree of inaccuracy always there, given the limitation of your data samples. And if you start to use a neural network for planning and control, or even use a traditional model-based planning and control, there's a degree of inaccuracy in those algorithms as well. And then you may have a noise in your actuators. If you think about eventually you implement those algorithms on software hardware, then there will be a disturbance to their execution in terms of software errors and sometimes long-term faults. Then if you look at the communication among vehicles, there's inherent disturbance to those wireless communications. And in this talk, given the time, I'll quickly go through some of the work we have done that relate to the sensor noise from the, and also a little bit from the input uncertainty, and relate to how we address the inaccuracy in perception and planning and control modules. So I will try to simplify the system and use this small example to illustrate. So if we look at what's showing here on the slide, we can think how we have right, a physical plant, and then we have observation, let's call it observation Y. This observation collected by the sensors will then go through our sensing and perception module, which will generate estimation of the system state, right? Let's call it system estimation X. Based on the estimation of the system state, the planning and the control module will decide what's the best control action to apply. We'll generate a control input U, right? So this is our typical end-to-end cyber physical systems with learning-based components embedding in it. And we have looked into two problems of this. First is for the sensing and perception module, if we have a disturbance in the input, either because of sensor noise or because of, in some cases, malicious attacks, right? So if we have this delta Y on top of your observation Y, how much will that change the state estimation? Right? How much your classification will be off? How much your estimation of the road boundary will be wrong, right? We want to estimate how much of that delta X is on state estimation. So this is the first part of the problem. Then the second part of the problem I'll talk about, then giving the state estimation with this delta X, can we actually analyze the system safety? So the first part of the problem, looking at the sensing and perception module, giving this delta Y, how do we analyze the delta X? This is what we call a robustness analysis problem against the adversarial attacks or against the random noise. And adversarial attacks have been studied extensively in the literature, where sort of researchers have looked into, right, if I input the image, if I add a small disturbance into it, like in the case showing here, the left is the original image, in the middle is the disturbance being added, in the right is what's looking into the human eye. It may look actually the same to us. However, it may for the neural network-based perception module, which will recognize something totally different, like all those examples will be recognized as ostrich, which obviously is wrong. So fundamentally, this problem, if we look at it as a mathematical problem, is if we give neural network and we give input X and its delta X around it, so we can view this X plus delta X as a compact input set, right? Capital X. Giving this sort of a small ball around your input, what would be the output be, right? How large your output range could be. This is what we call output range analysis problem. And we would like to have either accurate estimation of the output range, or at least some kind of accurate over approximation of it. And in the literature, a number of approaches have been proposed from the early approach based on so-called interval relaxation, where we view the input as a input range. But when the input is giving a range, we estimate how large the output range is for each neurons in the neural network, right? So sort of you over approximate each activation function, each neuron as a rectangle. Then you sort of propagate this through your entire neural network. This is obviously very efficient analysis, but the inaccuracy is pretty high. What will often happen is at the end, when you obtain the delta X, the delta would be too large to be useful for safety analysis. So there are approaches that try to improve on it. For instance, use LP relaxation, where you use a linear polytope to approximate the neurons, where you calculate the left and right derivative for each neuron's activation function. In our work recently, what we did was just one improvement on this. Instead of using LP relaxation, we try to use MLP relaxation, where we will divide the input into multiple segments, and for each segment, we use a linear polytope to approximate it. Now, the key here is to sort of navigate, right, the trade-off between what are the neurons where you want to actually use this more expensive MLP relaxation to analyze, versus the other ones who probably leave it, still use LP relaxation for speed. So this is sort of a typical problem we are very familiar, I think, in design automation community. How do we balance the trade-off between sort of approximation accuracy and the analysis complexity? And we have developed a number of techniques to do that, and was able to improve upon state-of-the-art tool. And then for the second problem, once you have this data estimation error delta X, how do we analyze the system safety, right? So in this case, it becomes what we call a safety verification problem of a neural network control system, right? So here we assume the planning and control module, they are also based on neural networks. And mathematically, this problem, again, it can be formulated a problem that's look familiar in a lot of the design automation problems, where we start with the initial set x0, right? Because now you're not start from a single state estimation x, but rather x with some kind of arrow delta x around it, right? Then we want to evaluate from here, giving certain time horizon or giving infinite time horizon. There are two types of analysis. Whether we can reach a target set without entering the predefined unsafe set. And this by itself is a very complex problem, and getting more complex because now the controller itself is a neural network. And we have done a serious work in this direction as well. From the early on, about 3 years ago, we proposed that EMSoft, this tool called Chen, where we approximate the entire neural network controller with a Boston polynomial. And then we apply reachability-based verification tool, FlowStar, on the polynomial-based controller, approximate the polynomial-based controller on the system dynamics. Then in the same year at ICCAD, we developed another method where we found that because of the complexity of verifying such system, the neural network control-based system is often quite complex. We found that if we are able to sort of reduce or minimize the Lipschitz constant of your neural network, then the verification would become much easier. So we proposed the controller distillation method, where we try to keep its regular performance, but also reduce its Lipschitz constant to enable easier verification, which we think is very critical for such safety critical system. The tool was further improved in 2020 with parallelization on GPUs, where we proposed Chen Star. Then this year we actually combined bursting polynomial with Taylor models, proposed a new tool called Polo, which just published this month, and where we were able to significantly actually improve the efficiency and the scalability of our tool. And so once this is the sort of a simple example of and a few of our approaches we have developed to address this problem of safety assurance with uncertainty, and where we sort of combine, right, the robustness analysis on the sensing and the perception module with the safety verification of the planning and control module, and put them together to do a end-to-end analysis of your cyber-physical system safety with the consideration of neural networks and the uncertainty in the system. And we apply this thinking into some practical examples, for instance, to autonomous driving examples. Although I have to say, given the complexity of this practical example, is it ultimately link-centering example? Even though we are able to use a similar thinking, similar methodology of estimating the uncertainty and then adapting the planning and control module, we were not able to provide any safety assurance because of complexity of the system. I think this is the open challenge, and we are very actively working on this. And if anybody else is interested, we're very much interested to discuss more. But we did try to provide those end-to-end assurance. In some cases, one way to try to sort of improve the efficiency is we are thinking a lot of those robust analysis was based on this notion of local robustness, right? Giving input disturbance around a particular given input state. How do we analyze how much the output will change, right? And then we do the safety verification. Because this is a local robustness, we have to do it at the runtime, and that's why the efficiency is a big challenge. So what if we can sort of break the loop, right? If we can analyze the so-called global robustness, where across all possible input space, giving a certain delta, we can analyze the maximum output delta. If we can do that, right, then we can do the robustness analysis offline, because it's across all input space anyway, right? And get the maximum delta Y, then apply safety verification. And we tried this, we call this global robustness. We had a paper this year at the date that was well received. And but the challenge, of course, for global robustness, you can imagine, is also itself on scalability. Even though we don't need to do it online, for offline analysis, so far we can only sort of analyze neural network up to sort of tensor neural, so it's a smaller CFA network. So this is still not up to the typical, right, neural network we use in practice. So that's still something we're actively working on trying to resolve. So Chen, how much time do I have?
Maybe in 1 or 2 minutes.
Okay, then I'll skip some. Then I'll just talk about the second issue. So the second challenge I mentioned is the lack of training data and their labels in such systems. For this, we looked into in another domain, in building control, in smart building control. And a few years back, we proposed a method to conduct deep reinforcement learning to learn an air conditioning control system or HVAC control system using deep reinforcement learning. And the result was pretty encouraging. However, what we observed and a lot of the follow-up work observed was to train that DRL-based controller well, you would need to sort of collect months or even years of data, which is not right practical. You cannot go to a building manager and say, deploy my controller and wait for 2 years. It will be very good. So since then, we have been trying to solve this issue. How do we enable reinforcement learning practice for this application, right? With very efficient learning, where we do not require a lot of data, or at least not a lot of sample label data. And we have done a serious work on this. In early on, we tried transport learning, where the key idea is we design a neural network where the front-end network is sort of building agnostic. The back-end network is the one that actually captures the building behavior, building specific characteristics. Then we do the transport learning, we only transfer the front end. That was showing to be effective in some cases. We also try to leverage the existing knowledge from the sort of domain experts. They can provide existing physics-based abstract models, and then we can leverage that to speed up our learning process. Especially such models can also help us to address the case where the data may be noisy, or when the data may be when the sensors may be faulty or maybe under attack. So we have a couple of works over the last 2 years on those as well. Given the time, I'll stop here. At the end, I think for this domain, we are showing that by using those sort of methods where we try to leverage the existing knowledge, we are able to reduce the data needed from years to first 2 months, but now to about a few weeks, to make it fairly practical, I think. All right, thank you, everybody. This is a knowledge page to my students and collaborators. Thanks.
All right, thanks, Qi, for the great talk. We have time for 1 or 2 questions. Do we have any questions from the audience? We have 1 question from Qixing Wang from Hong Kong Polytech University. The question is, the neural network reachability analysis is a great idea. Are there any time cost or scalability evaluation figures?
So yes, so indeed, we have, so let me go back to here. So we have done a serious work. Initially, when we were trying to use ReachN, and even later using ReachN Plus, which has improved quite a bit in terms of its scalability by using a bunch of engineering techniques like parallelization on GPU and all that. With all that, the degree of systems, the dimension of the system we can address was still fairly small, around up to, I would say, 5 to 6 dimensions, maybe. And so I would say those are still fairly small control systems. And Qixing, I know, I mean, you worked on verification problem of dynamic systems. You probably know that this is a sort of open challenge facing formal methods community, and a lot of the systems where people have been able to verify around this site, and which is not sufficient. I think in practice, especially for the sort of systems we are commonly seeing, right, in those LE-CPS, like robotic system and all that, we often see dimensions larger than 10 or 20 or even larger, even with abstraction. Polar, this most recent work significantly improved the efficiency and the scalability. We were able to actually verify some of the system with dimension higher than 10 or even close to 20 in some cases, but not all of them. It really depends on systems themselves as well. And in terms of time cost, when I say, right, we are able to verify, this is still like offline verification that takes hours or even longer. If we try to enable runtime verification, then even with Polar, I think we cannot solve maybe dimension higher than 10. It would be much smaller than that. So this is still an open challenge. This is something I think, frankly, I think about it almost every day. How do we solve this issue to really scale up while still providing some level of safety assurance? I increasingly feel like we may not be able to provide 100% safety assurance in some of those cases. And that may not be the right question to ask anyway, because right in the real physical system, it's very difficult to define a system dynamics that's 100% accurate anyway. So even if you are able to prove it's 100% safe, it's not really 100% safe in practice. So there has to be other ways to solve that, and we are exploring a few other directions. If you're interested, we can discuss more offline. Thanks for the question.
Thank you. Hey, maybe for the sake of the time, let's thank Qi again.
Thank you.
Okay. Our second speaker is Chen. He received his PhD degree from University of Michigan, Ann Arbor. He is now a professor in Zhejiang University with research focus on software hardware co-design, hardware acceleration, and power signal integrity. Dr. Zhuo has published over 150 technical publications and received 4 Best Paper Award nominations, including DAC and ICCAT. He also received ACM SIGDA Technical Leadership Award and Meritorious Service Award, JSPS Invitation Fellowship, and Humboldt Fellowship for Experienced Researchers. Dr. Zhuo has served as the organization and the technical program committee of over 30 international conferences and served as associate editor for IEEE, ICCAT, TCAT, ACM, TODAES, and elsewhere integration. He is a senior member of IEEE and a fellow of IET. Without further ado, let's welcome Professor Chen Zhuo to give us a talk on deployment of heterogeneous federated learning EEDA, an example on lithography hotspot detection, which is also a very timely and hot topic. Okay. You please unmute yourself, Chen.
Yeah, can you hear me?
Yep.
Okay, yeah, thanks for introduction. So let me share the screen. Can you see it? Could you see my screen?
Yep.
Okay.
Perfect.
First, I really appreciate that invitation for me to join this forum and to discuss our recent work. And I think it's actually very interesting to have such a cross-domain forum between the embedded system and design automation. And the two communities actually has already sparked and will continue sparking more interesting, exciting ideas. I think that Professor Zhu already presented something very interesting. So today I'm just want to talk about our recent work on deployment of the federated learning, which is very popular, I think, especially in the mobile community. And we want to see how it can be deployed in EDA and what is the challenges and what is the benefits we can get from the deployment. So actually, I think Professor Zhu already gave very interesting talk about what embedded system and versus data automation, and he covered most of what I would say. And I think you can see from the left is the embedded system. I think there's a trend that is the system side is like going more deeper, link right. They want to because now the system actually has very limited margins in terms of the different FOMs and the cost. So they're ready to link right for additional gains. They want to get additional gains, the BOM cost and FOM. On the right, on the other hand, on the right side, that's actually what the automation side want to do. In the past, actually, we have very very water flow layer by layer design methodology. And now, actually, we want to have like more insights and actually more direct communication with the system side. We want to link left for the agent design. You give me the system specification, and we can give you the design back. So this figure is actually from the IDEO and the POSH program of DARPA. It is called the DARPA Dream. You can get design in 24 hours. I think eventually the two sides will communicate and reach both goals. However, there's still many challenges. We want to deploy some embedded system techniques or want to deliver the embedded system specs directly to design automation. Those challenges are not limited to model, data, and algorithm. And today, so we want to talk about how what we see when we deploy a federated learning, which is actually a very popular, hot, and mature algorithm. We want to use that in the data automation problems. First, I want to start with some like chip design by AI, some background. So deep learning itself has shown very great potential in various applications. I think a very famous example is the AlphaGo in 2016. You know, we typically know that the number of the states for Go, the chess game, is like 10 to the 360. So it's a very large space. And so it is actually very surprising for many people to see that the AlphaGo can exceed a top human player, Li Shishi from Korea, in 2016 with like a 4-1 win. After that, I think the people recognize the potential of the deep learning and the reinforced learning, and they deploy those algorithms in various aspects. And a very recent example that is highly related to the automation community is the deployment of the reinforced learning in the chip placement. So from the figure on the left, you can see the number of states for chip design is actually much larger than the number of states for Go, which can easily exceed 10 to the 100K. However, with the reinforced learning that Google presented in last year's Nature, you can see from the figure on the lower right, it not only exceeds the conventional design automation tool, but also exceeds human being in terms of delay, power, and area. Of course, there are still many ideal assumptions and tricks behind such a solution, but I think the result itself is actually very impressive, and it further attracts many people trying to not only design a chip, an AI chip, but also to have the chip designed by AI itself. Behind such a very attractive results, actually there are still some hidden questions. I think one hidden question is, where does the quality training data come from? So for the Google's paper, I think they used like more than 10 or maybe 100 around chip data to train just the one chip design. So this is actually very difficult. Ideally, and what is more difficult than that is ideally, as you can see from the figure on the left, we want the data to be centralized, homogeneous, and sufficient to have a very robust trained deep learning model. However, in reality, as we can see for the figure on the right, design house is distributed all around the world. And each design house, they may have their unique products on chips, tablets, and the embedded system, CPS products. And moreover, the data, usually the data actually are local, it's not shared. The data are heterogeneous. And more importantly, the data actually are insufficient. We usually don't have like a zero rate to use like the data from maybe 40 or 50 chips of the for similar design specs to design one chip. That's not impossible in reality. So if we understand the design house, each is a data island. Each design house may have their own confidential and highly heterogeneous chip design data. Of course, we can have like a few commonly used strategies to resolve the problem. One is that we just use what I have. We just use the local learning method. Use the data at my own design house to design to train a model and design chip. Of course, a few challenges we need to figure out is that the design house itself can be resource constrained, and that the private data itself is insufficient. It's actually very difficult to use like 1 or 2 chip data to train a well-designed model for the chip migration. So it then becomes challenging to build a general and robust model if we use a local learning strategy. On the other hand, we can have like a commonly used centralized learning strategy, which means that we can have a very large, huge public data center that can collect design data from different design houses. But who will be this who will own this data center is a big question. It's difficult to have this data center just owned by government or owned by the automation company. Companies, design houses will have concerns of sharing such sensitive design data. That's one hand. And another hand is that usually the chip design data is huge. The GDS file for one chip design can be easily be TB or even larger than that. So sending such data to a public the data center can be very costly. And more importantly, that when this centralized learning involves multiple different design houses, they actually need agreement among all design houses, which is almost impossible. So as you can see from the last few slides, either local learning or centralized learning can be very challenging to realize our goal to address the issue of data. So recently, the popularity of federated learning actually gave us a possible alternative. Federated learning is used to collaboratively train a learning model while keeping the data as local. I think that's why it was proposed. So here I will give you a very short example about some background of federated learning. As you can see that we have like a centralized server and we have some local clients. It was first proposed for the mobile applications. And the centralized server will initialize a model, and then each local client will make an update using its local data set. Then the parties can share the local updates to the centralized centralized node. They just need to send the model instead of data itself, and then the centralized node can use all the local updates for aggregation. After the server aggregates all the updates, it will send back the updated model to each local server. And then each local server can use the updated model for local updates and for the local deployment. So there is a few interesting things that in such a federated learning framework. First, that the data will not be directly shared. Of course, there are still some privacy concerns, but anyway, the data is not directly shared by different design houses and by the centralized server. So that's actually partially resolved the issue of the privacy and communication cost. Second is that the centralized server actually can utilize the data or the model from different local nodes to train a more robust model with more data. So that also partially solve the issue of the data insufficiency. So it seems that the federated learning is very promising to resolve many issues that we will meet when we're deploying an AI algorithm, we're deploying a learning algorithm in the chip design area. However, it seems like there's still many hidden problems behind this federated learning framework. I think the one on the left is the federated average algorithm. Its advantage is to break the data island by keeping data local, as I mentioned, and also protect data privacy. Its disadvantage is that it generates a unified model for all design houses, which is not many design houses want. And then the large performance actually degrades for the data heterogeneity. So we summarize the challenges. If we want to directly deploy federated learning into design automation, there are actually a couple of challenges. The first one is the design houses may use the same technology from the same foundry, but have unique layouts and topologies. Such a phenomenon actually will create many unique data, or it's called non-RID data, that can be very difficult to be used and actually slow to be trained. And the second part is that the layout size itself is huge. As mentioned, it can be terabytes, but the number of the layouts, the quantity is actually small. So we still need to figure out a way to increase the quantity of the chip data to ensure that during training, the chip data is sufficient. The third one is that the different design house may have a different design performance. preference, sorry. So one size fits all policy will not work well. And most design houses are actually unwilling to follow the same updated policy. So some design houses may want to update more frequently than the others. So all those aspects actually brings different heterogeneous models, heterogeneous data, and heterogeneous communication requests. So that's actually a very huge problem that needs to be addressed if we want to deploy the federated learning in the design automation community. Design automation problems. Here we want to see what we use the lithography hotspot detection as a detailed example to see how we address some of those problems, and there are still many are remaining. Some background about the lithography hotspot detection. So we know that usually after we finish the layout, we need to go design rule checking. And after design rule checking, actually we need to further check if there are some lithography hotspots. And then we can do the mask optimization. Here is a figure to show some pre-OPC and post-OPC and hotspot on wafer. As you can see, even though at pre-OPC stage, we want to have a very square routing, but after the for the wires on the spot, it can be very rounding, and which may cause unwanted connection between different wires, and this can be very dangerous. So we usually need to do some like lithography optimization and also hotspot detection to find those dangerous spots and then to optimize them to prevent any potential issues. Usually such hotspot detection is completed by lithography simulation, which conducts like the 3D EM based simulation, which can be very time consuming and CPU intensive. Here we want to use federated learning method to detect such hotspots instead of using like a computer simulation. This can be a step that can be placed before the lithography simulation to avoid repeated simulation at the same runtime. And this is like the overall framework we proposed. So basically we have like a heterogeneous federated learning, which is a centralized server. It will get the local updates to do the global aggregation. And then each local server, each design house can do local adaptation to train their own unique models. And we also involve an additional feature selection step. This step will help us to ensure that we have sufficient local data. So as you can see, the aggregation adaptation will help to address the issue of the non-ID and allow customized model, while the feature selection allows us to have sufficient local data. So I will quickly go through those steps. Here I just summarized what I mentioned, the 3 steps: the feature selection, global aggregation, and the local adaptation. The feature selection is capture the most critical features component to alleviate to help mitigate the data heterogeneity. A very typical example is that we may have data from different technologies, 28, 20 nanometer, but both design can be of the same design, but different technology. How to remove the impact of technology to have more data is a problem. So we can use the feature selection to do something like a normalization to remove those impacts. And the global aggregation is actually to learn information from all the data sources. We want to say that, for example, if different design houses are using the technology from the same foundry, we want to say that if there's some common information that can be extracted to build a global model. And then local adaptation allows us to further tune this global model to have more customized flavor to ensure that the model can fit the local needs. And first for the feature generation and feature selection, we from very left, we have very complete layout. And this layout can be huge with terabytes of size. And we'll first clip layout into small pieces. And then with this clip layout, we actually have like more data, sufficient data to ensure the training procedure. Each clip data can be converted to an array based on its density and its wire location. And then this array is like this numerical array can be further converted with the DCT or DWT to DCT coefficients. For this DCT coefficients, as you can see that if we have an array maybe 16 by 16, we still have like 256 coefficients. So we need we employ additional channel-wise group lasso penalty to filter out the non-critical features, so that we can change the number of features from the maybe hundreds to only tens of features. After this step of the feature selection, we actually convert each layout clip to a small array of tens to maybe around tens of features. And this feature will be used for the model local training and global aggregation. So each client model can be further decomposed to a global part and local submodels. The global aggregation actually will try to train a global submodel by using all the information shared by different design houses. Meanwhile, the design house itself will try to adapt a local submodel to ensure that it meets its own customized requirements of the performance, power, and area. After the global aggregation, the centralized server will broadcast the latest global submodel parameters to all the clients. And the clients then further collect both the global submodel and local submodel for a few more updates. This is an example of a used local model, a custom client model. As you can see that we can have the first few convolution layer as the global parameters for the global submodel, and the last few fully connect layers as the local submodels. And there's actually some tuning. We can try to understand that what's the portion of the local submodel versus the global submodel to meet the required performance. Here in this example, we only have the last fully connected layer. And in addition to the model heterogeneity, we also need to consider the communication side. So different design houses may want to have different update rates while ensuring a good convergence. Even with the proposed global submodel division, we can prove a good convergence rate. For the synchronized updates, we can keep the same strategy as the commonly used federated learning. And for the asynchronized updates, the central server actually collects outputs only for the first key responded clients. So we don't want to continue waiting for all the clients to respond. We want to wait for the first K. And then we have like a ratio of A over AK for the global aggregation. Here we have some experimental results on this federated learning that we customize for the lithography hotspot detection. And we have two data sets. One is from the ICCAD. It's like a publicly released sets into the 8 nanometer. Another benchmark is from industry, which is like an in-house data set that's in 20 nanometer. Here is some information of the size of clips, number of the training and testing sets we divided. And we compare with the 3 algorithms. One is the federated average. That is the mostly cited federated learning algorithm. And we also have the fedprox that as a proximal term to the objective to handle such a heterogeneity. And we also have local learning that is supposed to, as long as the number of data is sufficient, that is supposed to work the best, but its robustness is always questionable because it doesn't have the information from the other design houses. So it's easy that this model can be overfitted. From the figure on the right, as you can see that the proposed HFLLA actually works best compared with both federated average and federated prox. The top one is accuracy on ICCAD and industry for the 4 clients. And the bottom one is the one for the industry case that we have like 10 design houses. And then we further compare the impact of the number of clients. So different number, the more clients we have, actually the model will be introduced the more heterogeneity. As you can see that the HFLLA actually can maintain pretty good accuracy across all the different number of clients. It's like a 7 to 11% accuracy improvement for both IC-CAD and industry cases. Meanwhile, the local training actually can also maintain very good accuracy because it only uses own data to train and then to test, but its robustness actually is not very good. That will be shown in the later slides. For both the federated average and the fed prox, actually its accuracy quickly dropped to maybe below 90%. And this figure shows the convergence rate among different methods on IC-CAD industry during training. For both the synchronized communication and asynchronized communication, the HFLA can ensure very good convergence rate, while the other method actually converge much slower than that. And this is an interesting comparison that we have like the synchronized updates and asynchronized updates. We first can see the clear correlation between the updated layer and the client average test accuracy at steady states. So the 80 of 6 means that when we have the local updates only on the last layer, the last conversion, the fully connected layer, and 82 to 5 means that we have updates from layer 2 to 5, and the 81 is that we have only the first layer to be updated. So in this figure, we can see that the last layer apparently has a large impact than the other layers. And however, when we go to the asynchronized updates, such impact is actually limited by the local adaptation. Finally, we want to study the impact of the heterogeneity. The industry case is actually more heterogeneous data set than IC-CAD. IC-CAD is more uniform. So the local learning can hardly capture such non-ID impact. As you can see from the figure on the left, it quickly dropped to 0.81 when we have a model trained by its own data. More heterogeneity is introduced to like 70 clients, then the performance of local training is actually pretty bad. On the other hand, you can see for the figure on the right, even though with more clients actually indicates that we have fewer data for each client. For the HFLA, we can still always maintain like more than 90% accuracy across all different number of clients. So I want to quickly summarize this work. So data insufficiency and privacy actually is the major concern for deploying many learning algorithms in the community of the EDA problems. This actually slowed down the successful deployment. And the federated learning actually is a very plausible and promising alternative, especially with popularity in mobile and embedded applications. But the uniqueness of EDA problems brings new challenges that will not be considered during its application in the mobile community. And here we use the lithography hotspot detection as a good example of the FL deployment. We try to address a few problems we mentioned in the data model and communication, but there are still many problems remaining that need to be addressed. That's all what I have for today. Thanks.
Okay, thanks, Chen, for the great talk. Do we have any questions from the audience?
Hello, I'm Guojie from Peking University. And Professor Chen, thanks for the great talk. And I have one question. So although federated learning is said to preserve privacy, so I assume there should be a lot of attack approaches to this federated learning. So although a user may not directly assess the hotspot pattern, but they may still possible to extract a few key parameters. So whether this is a risk.
Yes, I think you're absolutely right. From the federated learning itself, there are already many papers that we can try to code the model to try to find the key parameters and then to have the privacy issue. And I think there are actually many works how to prevent that, about adding the noise into the shared model and like the differential privacy. I think those additional techniques can be always added to this framework to make them more robust. Regarding the federating itself, I think it's I think the main challenge is still like the data insufficiency, how to protect that. At least the federated learning framework help us to show a promising way that how design houses can share their own and private data to build a more robust model, so that we don't need to be puzzled by the data insufficiency, how to get a learning model.
Okay, thanks.
Okay, due to the time limits, let's thank Professor Chen again.
Yeah, thanks.
Can quit the screen share.
Yeah, I'm trying to. Where is the screen share? Give me a minute. Okay, got it. How to start?
Okay, our next speaker is Professor Guojie Luo, who is currently Associate Professor at the School of Computer Science and Center for Energy Efficient Computing and Application in Peking University. Professor Guojie Luo received his bachelor degree from Peking University and PhD from UCLA. He got the 2013 ACM CTA Outstanding PhD Dissertation Award in electronic design automation, and the 2017 ASP DAC 10-year retrospective most influential paper award. His current research interests include design automation for emerging computer architectures. Without further ado, let's welcome Professor Guojie Luo.
Thanks for the invitation and introduction. So today we'll talk about our thoughts on the intersection between embedded system and design automation. So the title is very big, but I will only present the challenges at the very end. So the title is towards automatic cross-layer design and analysis of reliable embedded systems. So as Professor Zhu said, so we have a lot of specialized processors in embedded systems. So like in automotive, so nowadays the electrical system in automotive is much more complicated than like 10 years, 20 years ago. And there are a lot of chips. And of course, there's some computational demands that we need to deliver compute-intensive tasks. And also on the right-hand side is a surgical robot. So we can see that we have the 3D image processor that a doctor can observe the robot arms, and then he can use his hand to control the robot arms. So we need a 3D image processor and also need a manipulator controller. So we need a lot of specialized processors in embedded systems. So although for the big domains, people see a lot of opportunities, and they of course will build ASIC for those domains. But how about for the small domains? So many applications may not afford building an ASIC, and people resort to GPU for data parallel computation. So this is a very well-known classification. So on the left-hand side, we have CPU for flexibility and programmability. And on the right-hand side, most right-hand side is the ASIC for latency and energy efficiency. And we propose this solution for the small domains. We believe that there's a long tail of applications, not super data parallel, but it's still possible using recoverability for non-universal but regular data flow. And our goal is to develop a library that can efficiently generate architecture and tools for new domain. And besides the recoverable architecture, we still want to maintain an option for the users to build an ASIC when the volume goes high. So how to achieve this goal? So how about we look at the modern Apigee architecture? So on the left-hand side is the Silex Versal ACAP. It's a modern Apigee architecture. So in fact, it's no longer a pure Apigee. The Apigee part is only this small region shown in the blue color. So it's a fine-grained recoverability array. You can think of it as a big level network of lookup tables that can implement logic function and flip-flops. So it can emulate like combinational circuits and sequential circuits. And in the modern Apigee architecture, there's also a lot of area occupied by the coarse grade array. So you can think of them as a one-level network of ALUs. And of course, there's some on-chip storage, and it can perform spatial computing and also temporal computing, but they are working tightly. So how to improve the design efficiency? So one is to increase the reuse. So in terms of architecture, so we assume we have a few stages in the design phases. So at the beginning, in early stage, we can get a commercial Apigee to implement the mixed grade array as an overlay. And then when we comes into a fast evolving stage, that means the algorithms are still changing. So to run the algorithm efficiently, we may harden some of the recoverable units. So this is the mixed grade recoverable array. And when we come to a stable stage of this domain, so we can build more accelerators, but we can still leave some coarse grade recoverability. So the most left-hand side for prototype, the middle one for early production, and the right one for the massive production. But all of them can have the same existence form, the mixed grade recoverable array. So on the left-hand side, we can implement this architecture as an Apigee overlay. And in the middle, we can just deliver as the IP. And on the right-hand side, we can decisively harden some of the to drop off some of the recoverability to train for efficiency, so that we can still have some flexibility. But if the volume goes high enough and the algorithm and application becomes stabilized, we still have an option to tape out a ASIC. So this is from the architectural support. And the second solution is from the methodologies support. And we adopt the concept and old concept like 30 years ago from the software engineering. It's called generative reuse. So what problem it solves? So it identifies that if we use the component we use, there's some problems. Either you may have a combinatorially exploding libraries, or your library have poor performance, or your library is marginally reusable. And in ideal case, we may need some partially specified precursor components. And how to do this? So people also propose solutions in the software engineering domain. And we use the domain-specific language technology to describe the problem space. And in the middle, we use the generator technology to codify the domain knowledge. And on the right-hand side, it generates an instance in the solution space, use the component technology. And how about we look at what's happening in academia for hardware design? We can see a similar trend. And this figure is from the paper from Stanford in IEEE Micron 2010. So it proposed have two phases to design a hardware and to design a chip. The phase one, design exploration and tuning. And this spanner and chisel symbol, so it's a generator that can fit in the architectural parameter and generate an an architecture for evaluation. So after the tuning is stabilized, and the phase 2 is to generate hardware and generate the verification environment. And how about Berkeley? So this is also get from the slides from this ISCA workshop on Agile and Open Hardware in 2019. So they propose instead of RTL code reuse or IP reuse, we can think about the generator reuse. So as shown on the right-hand side, the spanner and chisel represent a generator. So instead of improving the RTL code, so we can generate the add more, we can change specs, add more features, improve the implementation, and generate verification and validation environment, so that we can have this iterative flow that is more agile to the changes of the specs. So to make use of this methodology is practicing in the recent decade. So so I summarize in this slide. So it's an effective paradigm for design reuse. So previously we have IP reuse and code reused, and now is the age of generator reuse. So what do we mean by the generator? It's a coherent set of generators. Although in most scenarios, if you read the papers, most people talking about the hardware generator, the spanner and chisel generate RTL code. But in fact, in the generator-based approach, instead of generators, there's some provided passes for the design optimization. And also there's some opportunity for user-specified passes to do the project-specified optimizations. So, so it will be customized for a new project efficiently. And then besides the hardware generation, in the ideal case, we should have the software generation, the verification generation, and configuration generation, and document generation in the ideal case. So in the next few slides, I will show 2 examples that we are practicing. Use this generator-based design approach to design a CGI generator and also the on-chip network generator. And at the end, we'll talk about how this relates to embedded system and how what is our future direction. So for the CGI generation, we adopt the Y-chart approach. It's very well known in the embedded system domain and design automation. And on the right-hand side, is the application, goes from this Y-chart, and left-hand side is the architectural description. So we have the application to DFG to fit in the flow, and then we also have an ArcGen to generate architecture. And then we have a CGI EEDA to map the DFG to the architecture. And after we get the map design, we can go through the classical EEDA to generate either an ASIC layout or Apigee BISTU. So to illustrate the ArcGen, so we can use the we design a Scala library that beyond chisel to describe the architecture efficiently. So we can describe and generate for the element blocks and also for the hierarchical blocks. And this figure illustrates how the architecture description performs in the whole flow. So the green box represents the architecture description that I just showed in the last slide. And in fact, there's 2 flows. One generates the hardware as shown in these blue arrows. So we generate physical constraints, generate chisel or fertile, and then use the spanner and chisel to generate RTL code to get a hardware. And besides, we also have the application, the software application. So the red arrows represent the software flow. So when we click the play button, we can generate a config that can run on this hardware. And we click the spanner and chisel button, we can generate the hardware. So in the generator-based design approach, we have a single source of truth, but there are multiple paths to generate a coherent system that can execute the functionality that we want. So here are some details, but I will skip this quickly. So this is just illustrate how we map data flow graph and so on the left-hand side to our hardware. So this is a very simplified hardware with only 2 ALU and 2 register. But we have a 3 operator, the plus, minus, and multiplication. So we need to extend it in time to have 2 cycles to complete this task. And then after a few mapping algorithm, we can decide which operator performs on which functional unit. So the generator-based approach can enable us to make the decision at the end, not in the library design stage. So for example, in this data flow graph shown on the left-hand side, we need to add the result from the subtraction and multiplication. And there's some multiple ways to do this. One is to have a synchronized data that we go a detour from the result of subtraction to have 3 cycles arrive at the input of the addition, so that it can synchronize with the multiplication. Besides, we can also use the hardware to do this synchronization. For example, we can get the results of subtraction earlier, but we wait for a few cycles. But this consumes hardware resources. And if we use a library-based approach, we need to build this synchronizer first, and then at the end we can only evaluate at the end. But if we use a generator-based approach, we can just use a parameterized generator and leave a decision whether we use a synchronizer or not at the very end. So using the generator-based approach, so like we can describe the solution space, whether we use a 3x3, 4x4 CJA, or whether we use a synchronizer or use a slack synchronizer, skew synchronizer. So there are different kinds of hardware with different power performance and area. So this design space, we do not need to finalize the architecture early, so we can leave some flexibility at the end. So until we have the applications to test, so that in this case, we test across 5 applications and find out that for this set of parameters, the 3x3 with skew synchronizer outperforms other solutions with 20% fewer resources and 30% higher mapping success rate. So this is only a very small example, but what we want to try to show is that using a generator-based approach, we can leave the decision to the end. And the second case is on-chip network generator. So due to the time limit, I just briefly go through this. So an on-chip network is more general than a NOC. So it includes a bus topology, point-to-point, and also a network topology. Usually, NOC only refers to packet switch on-chip network. And here, we also practice the generator-based approach. So the single source of truth is the network model. And this flow on right generates a hardware. And for on-chip network, it's very interesting because it has a lot of software-like techniques. For example, whether we use for routers, whether we use a packet switch or circuit switch, and then we also have some flow control strategy, and also we have different kinds of routing algorithm. So it seems very like software, right? We have routing algorithm, but if we look into the detail of the on-chip network, we find out that there are also different kinds of routers. For example, we have a distributed router that the routing algorithm is hard-coded. It's hard-coded in the router itself. So the routing algorithm is part of the hardware. And the source routing, the routing algorithm perform in the source node, and the path is encoded in the packet. And the last case is a circuit switch. So although the behavior is configured in the router itself, but the decision is made at the compile time. So we can see that we have different, very different options of routers. And although the routing algorithm is software itself, but when it comes to on-chip network, there are multiple ways to implement this routing algorithm. Part of them may be hardware, part of them may be software. And then which one is suited for our current situation? Sometimes we may not know before we actually run the application. So using a generator-based approach, we can leave these options to the end, propose the decision to the end. And then there's some data to illustrate the quality of our generator. For example, at 3 PTK 45 nanometer, this is not the latest number, so we can run as fast as 500 megahertz. And then the latency is faster than other existing open source on-chip level generator. And also the generator-based approach enables us to evaluate different, very different kinds of algorithm. So we can fit the algorithm in the generator that it can generate hardware automatically. But which algorithm to use, we can postpone the solution to the end. So these two projects we already posted on GitHub. If you are interested, you can search Pillars and Perlin, one for CCI generation and the other for the on-chip level generation. So it's also listed in the CHISO user community. Yeah, and then and our next step is to get a fully working mixed-grade recombinable array generator, because currently we can generate circuit switch, recombinable logic, packet switch, and recombinable PE. So we can, after we get the whole flow working, so we are expect to be a kind of replacement of the Silas Apigee. But of course, we are not competing with them. We only targeting at the domain that the Silas Apigee may not be the best suited for. So we can tune our architecture for those small domains. And then to come back to the beginning of slides, right? So we have the specialized processor in embedded systems, but what are the problems? So here is a case. We know that some like smart cars, they have some accidents. So this is one example. Ideally, it may execute this program when accident happens. So if the airbag inflates, will unlock all doors, unlock the trunk, and extends all door handles, so that the people from outside can help the driver to get out of the risk. But what happens if the electricity is down? When the electricity is broken, the whole program cannot work. So it's very complicated. Not only we need to verify the code itself, but we need a coherent system to work on. Yeah. So to combine these two, this is our directions that we look into. So for the generator-based MGIA design methodology plus reliability, the opportunity is that MGIA has inherent redundancy, right? We have a lot of units, so it has inherent redundancy. And the generator approach, as shown on the figure on the lower left corner, we have a single source of truth. So we can not only generate hardware, generate software, but also generate the models for verification. But of course, there are a lot of challenges. We need some cross-layer consideration. So as the example showed last time, we also need to consider the physical environment. And for the cyber environment, the application, compiler, architecture, and device, all this creates some complexity. And the current generators mostly focus on digital, and we need the modeling with analog digital interaction and physical cyber interaction. And also Professor Zhu mentioned currently many workload in deep learning. So deep learning model is inherently resilient to numerical errors, but there are also new challenges in its robustness and vulnerability. So how it affects the full software hardware stack decision. So we will be interested to build a generator-based approach to study this in the full stack. And the last challenge, as I mentioned, for the generator-based approach, we can postpone the decision of reliability options in all levels to the system level. But in this case, we need effective design space exploration. And what we need is an automation tool for failure analysis and synthesis, we need to consider this reliability for embedded system. And this is a tool published in 2011. So start from some model, you can generate abstract model, generate some fault sheet, and do a fault sheet analysis, and then do the FMEA generation for people to improve the design. So apparently it's not fully automated. And if we put it into the generator-based approach, we have some opportunity to get a automated flow. But of course, it's not everything. It's not everything because, as I said, a generator-based approach is most suited for the digital world. And if we need to interact with the physical world, we need more efforts to build the models for physical and analog part. But for digital itself, this may be possible to get an automated flow to analyze the faults and then to improve the design. And because the generator-based approach, we have a single source of truth that makes this iteration convenient. Okay, so to summarize the talk, we have a new practice of the generator-based approach, and we talk about why we investigate the mixed-grade generators, mixed-grade recombinant array generators, and we briefly talk about our CGI generator and on-chip network generator. And our ongoing work is to deliver mixed-grade recombinant array generator. It's not only the hardware generator, but it also generate scheduler, mapper, configuration, verification, and documents. And in the ideal case, not only for PPA, and also consider the reliability and dependability in the whole flow. Okay, so that's the end of my talk. Thank you for listening.
Okay, thanks, Guojie, for the really wonderful talk. I apologize because we are really running behind the schedule, so maybe we have to skip the Q&A, and let's continue. Okay, our last invited talk will be given by Professor Nan Guan. So Professor Nan Guan is currently Associate Professor at Department of Computer Science, City University of Hong Kong. He obtained his PhD from Uppsala University, Sweden. His research interests include real-time embedded system, autonomous system, CPS, IoT. He received his ACM early career researcher award in 2020, EEDA outstanding dissertation award in 2014, best paper award from EMSoft 2020, 19, and multiple times. That's a wonderful achievement. He is also a general chair of RTAS 2022, program chair of ESWeek 2022, RTS 2021, and so on. He served in the execution committee of IEEE technical committee of real-time systems. He will be talking about the embedded software platform aspect of autonomous machine design automation. Without further ado, let's welcome.
All right. Yeah. Thank you, Chenren, for inviting me and the introduction. So here, I guess I will, because the time is really limited, I will briefly talk about a very small aspect in the design automation, which is about the embedded software platform for design automation of the autonomous machines. So by autonomous machines, basically, I mean like different types of machines which can perceive the surrounding environments and can do the decision and do the corresponding reactions. For example, the autonomous vehicles and the drones and a lot of different types of robotics. So because I think today we are seeing more and more these kind of machines are like running in our society, and probably in the future we will see like tremendous different types of autonomous machines. And the topic of today is, of course, about design automation. So for the software deployed on autonomous machines, so like, is it the opportunity to use design automation techniques to get the benefit? Of course, here, it doesn't necessarily mean that we just press the button and the software is ready. So I guess what is realistic is to, as much as possible, to leverage the techniques from the design automation, therefore to improve the development efficiency and also the quality of the software. So why this is possible or this is needed? So first, by doing this, we can greatly improve the development efficiency, because a lot of these kind of machines, they share a very similar structure. So basically, they are all data flow systems, and also they share a lot of functionalities. Okay, so they all do perceptions, and they just deliver the data to the next component, do the planning, do the prediction, and so on. So instead of reinventing the view for each single product, it is good to have a like sort of shared foundation, shared platform. Therefore, everybody can easily to develop like the smart machines without worrying about all these system level difficulties. And also, like, if we can enable the design automation, and the big benefit is we can greatly improve the correctness assurance of this kind of machine, because by the model-based design approach, actually we can already make the system much more reliable, because we start with a sound model, and based on this sound model, we can make the system correct by design instead of building the system bottom up, and we have to deal with all these details, all these implementation issues, and so on. So because I mainly work on real-time systems, so of course my concern is mainly focused on the timing aspect. So even if your software is functionally correct, so you have to also make sure it is timingly correct, because otherwise, if your perception or your decision results are delivered too late, then it's still useless. So in order to guarantee this, usually we work on some model, right? So we look into the system behavior, and we want to guarantee that, okay, so the response time is not exceeding the expectation. Okay, and after that, we can like sort of realize and implement the system, and to synthesize the software, for example, or map the functionalities to the software and hardware platform. So over the years, like people in the real-time research community and also in the embedded system research community has done tremendous work doing with many different kinds of models. Okay, so for example, many systems can be described as something like a graph-based model, described as a DAG. Then we can do a lot of analysis, a very elegant results exist, so we can very quickly decide if the model of the system satisfy the required timing constraint. If this is not the case, then we need to revise the design. If this is the case, then we can like start to implement the system. Okay, so then we hopefully we can transfer a correct model into the software and deploy on the hardware. Okay, so this is sort of our assumption in the work in the past several decades. But actually, this is not the complete story, because obviously for non-trivial embedded systems, for example, like this autonomous machines, no one would afford to develop everything on bare metal. Okay, so everybody will use some kind of software platform. So therefore, if you have an ideal model, then you synthesize the model. The code has to fit into certain software platform. I think actually this may not be a very theoretical aspect in the research, but this is actually a very important piece that is missing in a lot of existing work. So for example, last year, so in a conference called ARTAS, there was a panel discussion, and we invited several people from both industry and academia, so to discuss about like, is it possible to sort of find some like standard or common software platform so everybody can work on it. This is like Android for like mobile device, right? So now today, if you want to do some research, if you like do not work on Android or iOS, if you work on some other operating system, probably no one will buy this, because people know this is even this is a good idea, but it will be not used forever, right? So if there's a like sort of standard software platform, then the work can be much better connected to reality, and probably can have a much realistic value. And like the people have like different discussions and propose different options, different possibilities. For example, I just take a small example, something called MIH, which is proposed by Honghai, which to serve as a general shared open framework for autonomous vehicles. Is that not only autonomous vehicles, but electronic vehicles. Okay, so I think so far I have been like talking about the background of the real content that I want to share today. From my personal point of view, so for autonomous machine, actually one of the promising software platform is ROS, Robotic Operating System. So this is exactly our group has been looking into in the past few years. So basically our vision is, yes, we have done a lot of theoretical work to do the analysis, to build beautiful models, and to do analysis for the models. But now I think this is the time to connect all these models to a realistic software platform. Therefore, hopefully our theoretical research can be easily transferred in real life. And I mean, so because I only have, I guess, a couple of minutes, so I guess I will do this very quickly. So ROS, this is, even it's called the operating system, but this is not really operating system. It's actually middleware. So you can install ROS on top of, for example, Linux or other real-time operating system. So it basically provides a framework, a very user-friendly interface to developers, that you can easily integrate the system, you can reuse others' components, and most importantly, ROS represents a huge ecosystem behind it. So there are tremendous tools and libraries and the simulators that you can use. So based on ROS, people can easily develop fairly complex robotics software and autonomous applications. And also ROS has been refactored to provide a much stronger real-time capability, and it's considered as a possible choice for autonomous vehicles. For example, there's the open foundation called AutoWare, which is built up on ROS, which provides a full stack solution for the software system of autonomous machines. So basically the point here is ROS is very popular, as it's very widely used, and it's very influential. And like this is many people are tied to this ecosystem. And so before, ROS doesn't have a very strong real-time capability, but currently they have a much better version, which has stronger real-time supports. Okay, and so now they are also improving their real-time functionality. So basically, the conclusion here is so in the past, ROS is usually considered as a toy system or a system for fast prototype, rapid prototype. But today, ROS is seriously has been used in reality for safe critical and even mission critical and even safe critical systems. Okay, so then based on ROS, we have done like some of the model-based real-time system design work. So now we are not working on a purely theoretical model, but we are really working on a model that is has a realistic correspondence in ROS. That means our model can be fully automated, translated, or mapped into the ROS app implementation. So this is very easy. This also thanks to the nice feature in ROS that ROS has a very elegant architecture that the computation and the communication are very well decoupled. Therefore, you have a, from the logical point of view, you have a very neat structure. Therefore, you don't need to worry about all those integration details too much, as long as you deal with the timing issues properly. And we have done some of these works, and we have working on modeling, understanding, and analyzing several important components in ROS. So we have a fairly good understanding of the behavior of the ROS. Therefore, we can start to do this kind of theoretical analysis works. Okay, and I don't think I have too much time to introduce this. Let me probably jump to the end. Okay, so so because the autonomous machines will be like even more significant tomorrow, so we have a great potential for the design automation in this domain, because like improving the development productivity, this is really important for the whole ecosystem. And we will not only work with the ideal models, but we will look into this realistic software platforms. And we propose that ROS is a promising software platform for this, and ourselves, and I hope more and more people will work on this like standard shared platform, so your research effort will be easily transferred into reality. Okay, yeah, I think I meet the deadline. I'm very happy with that. Yeah, thank you very much.
Thank you so much, Professor Nan. Yeah. Okay, I think we are kind of chasing a little bit back to the schedule, and let's maybe take a 4 minutes break, and we will have the exciting panel session. By the way, during the break, if you have any, for the audience, if you have any questions, feel free to chat with our invited speakers. Let's come back in 4 minutes.
Thanks, Nan. Are you still there? Can I ask you a question?
Yes, of course.
Right. Thanks for the very interesting presentation. So for ROS, have you guys tried sort of analyzing its timing behavior over like truly distributed system, where it's communication, maybe a wireless communication?
Right. So first, currently we haven't really done anything with that, because this is quite difficult, because this involves like different layers, right, in the communication. And what we did look into is on the DDS middleware layer. Okay, so we try to understand what is the capability can be provided by DDS, because one reason like people claim ROS2 is has much better real-time performance is because people believe DDS is a real-time like communication like middleware or protocol, right? So because it at least supports some QoS features and so on. So this is one thing that we look into. Like we want to try to understand how we can sort of connect all those QoS features with the ROS performance guarantee features, and to make them into the same loop. This is one aspect. The other aspect is we are trying to understand. So because DDS is a very heavy stack, so you have to run it on the processor, and then they have a lot of resource contentions, and we have tried to understand what other like performance degrade due to this contentions. But below the DDS layer, we didn't really look into that.
Got it. This is really interesting. Yeah, I had the discussion with other people on DDS and how challenging it is, and we are looking to some of the applications where we are thinking where the ROS can be deployed in a more distributed manner. But even on a single machine, I think there's plenty of interesting problems to look at. Thanks a lot. So I'll probably follow up with you more questions later.
Yeah, that's great. That's, of course, yeah, that's great.
All right.
Please sit here. Okay. Welcome to the second part of the workshop. Chen, can you hear me? Chen?
Yeah, I can hear you well.
Okay, let's start. Hello, everyone. Today, we will have a panel with 4 panelists. First, please allow me to give some brief introduction to them. The first panelist is Professor Jie Liu from Harbin Institute of Technology, Shenzhen. He is the Dean of AI Research Institute in HIT. Before joining HIT, he spent 18 years at Xerox PARC and Microsoft. His research interests include sensor network, AIoT, and energy-efficient computing. The second panelist is Professor Naijun Zhan, comes from Institute of Software, Chinese Academy of Science. His research interests cover formal design of real-time embedded and hybrid systems, program verification, concurrent computing models, and model and temporal logics. The third panelist is Professor Li Jiang, who is an associate professor from Shanghai Jiaotong University. He has published more than 90 papers in top-tier conferences like the computer architecture, EEDA, and the AI conferences. Several technologies proposed by him has been in commercial use in cooperation with TSMC, Huawei, and Alibaba. He received ACM Shanghai Rising Star Award and CCF WSI Early Career Award in 2019. The last panelist is Mr. Song Yao. He is currently the co-founder and CEO of Orange Space. He was the CEO of DeFi Tech, a startup that provided efficient deep learning computing platform for smart city and self-driving applications, which was acquired by Xilinx for over $300 million. Song founded Orange Space in 2020 to develop gravity series launch vehicles and provide cost-effective launch services to worldwide customers. The first rocket of Orange Space Gravity 2 medium launch vehicle will be launched in next year. Song has received many rewards, including first prize of technological invention of China Computer Federation, Forbes 30 under 30, and MIT TR 35 innovators in China. Okay, so welcome all the panelists. So we will start. Okay, we will start the first question. So because the 4 panelists have different background, the first 2 professors are from the universities or institutes, and the third panelist have the background from the currently works for both universities and the industry, and the final Mr. Song Yao is from the industry. So we have firstly we will have a very direct question. So because the topic of this panel is about the cross of between the embedded systems and design automation. So the first question is, what design automation tools are you using for your embedded system products or research? Okay, Professor Liu, can you give some of your comments or opinions?
Hi, yeah, this is Jie Liu, and very nice to be here. And well, frankly, I don't use any these days because just kidding. But we use a lot of design tools. And many of them has has some automation properties like the layout tools and checking tools and so on. I don't think we go so much beyond the common ones, like the circuit design tools and compilers and stuff like that. And these days we focus a little more than typical sort of hardware type of embedded systems. We also do quite a bit of AI based or data-driven design. For those, we use some high-level tools like TensorFlow, PyTorch type of things, mainly for training. I won't call that too much of a design tool, but it's a way of expressing the models and train the models and deploy them. And we also do ourselves a design tool that it's actually has a bit of history from my Ptolemy days. So we are picking that up to rebuild it into a system level design and simulation tool with some of the synthesis, software synthesis techniques in it. We try to use that as a way of integrating AI and cloud computing and edge computing together to be a sort of AIoT or a cyber physical system design tools that embrace model-based and data-driven designs. So that's where we are. And yeah, in particular, we do very little hardware or chip type of designs these days. So I have little to say on that front. Yeah.
Okay.
Get back to you.
Okay, thank you. The second time is the Professor Naibing Zhang. I know that you are an expert in the domain of the formal verification, and you have also some collaborations with some aerospace department. So can you share some of your experience?
Okay, thanks, Mingsong. Thanks a lot for inviting me to be here. Actually, you see that in the past decades, I worked on developing a toolchain similar to SCADE for design safety critical embedded system. In detail, actually, you see the toolchain consists of modeling. Currently, we use the combination AEDL and Simulink and state flow. Actually, we are trying to integrate these two stuff together and develop a simulation tool for the combination. For the verification for safety critical, so we are trying to do the verification of the combination, the models represented by the combination. So we use a hybrid CSP. Actually, is an extension of a CSP, which is commonly used in concurrent computation model. To the hybrid systems, we try to transfer automatically from the graphical model given by the combination of AEDL and the Simulink state flow to the formal model given by the HCSP. For the verification, you see that we extend the Hall logic to a hybrid system. We call it a hybrid Hall logic. For the verification based on theorem proving, we develop a theorem prover for the hybrid Hall logic based on Isabella Hall, which is a very popular theorem prover. Definitely for this step, you see that the hardest part is the invariant generation. For invariant generation, we designed several approaches for invariant generation automatically. For this procedure, we called some of the existing tools like Z3 for the certified BD modular series developed by the Microsoft. The other two you see that for the environment generation, also for some controller synthesis, it heavily depends on some optimization technique. So we have two course, several optimization technique, particularly convex optimization technique, like the mosaic and other SP servers and so on. Finally, we are trying to generate code from the verified formal model from HSSP to some of the real programming language like the System C and the C code. We also consider as a future work, we consider how to translate the verified HSSP model to the raster. So yeah, so that's actually this tool chain has been applied to some of the design of the spacecrafts, as Mingsong mentioned. Yeah, for example, the Chang'e 3 and so on. Also for the Mars Explorer, like the Tianwen 1. Okay, that's it. Yeah.
Okay, thank you. You mean that you use the design automation tools you developed, right?
Yeah.
And on many safety critical applications, right?
Right. Yeah.
Oh, okay, thank you. Okay, Professor Li Zhang.
Okay, I'm trying to keep it short. So most likely we just as most of I think as most of the researchers in my domain, I mainly work in the cross section about the AI algorithm and architecture, including the compiler frameworks. So I will use a lot of them are open source, especially on the software part. Like GVM, Mingsong, these are the AI compiler frameworks. We will, put our ideas or new contributions upon these open source platforms. And also for the architecture exploration, we will use like Gen5 and all other different kinds of like processing memory, those simulations. So these are mainly for the exploration of opportunities like accelerations or this kind of thing. Then when you go to more, detailed evaluation or assessment about the true, benefits you can get from these designs, we will use more, formal or industry tools like design compiler or these kind of EEDA tools until we get some chip take out. So this is in my research. So in the company, I think it's similar. In some of the department, our mainly research department, they are, especially in the embedded system domain, it's a very tight, coupled system. It's not like a general computing system. We have a very clear, abstraction layers on top of each other. But in embedded system, you can have a lot of, aggressive optimizations like software, hardware, co-design, co-optimizations. So for this kind of exploration, we have to use some very lightweight design tools or evaluation tools like Gen5 to explore the opportunity. Then when you get enough benefit, you can hand it over to like chip design department, like the high silicon. They will use a very formal, industry tools to implement. Yeah, that's all. Okay, so but sometimes we also develop our own tools, like especially in AI research, the algorithm is open, right? You can design different kind of algorithm, including how you train it, how you do the compression, and these techniques also need to be coupled with hardware features. Hardware will have to be supported. So these kind of different tools have to be get into a loop. Then you can do the optimization.
Okay, thank you. I know that you did a lot of work in the AI chip design, right? So you also mentioned, for example, when you there are some automation tools for the AI, the AI models. You use the TVM to find the best architecture of the network. And then you need a lot. You use other tools like the Gen5 for the CPU simulation, right?
Yeah.
So does that mean the people in your domain need to learn or need to learn a lot different kinds of design automation tools?
Yeah, because it's a heterogeneous computing system.
Okay.
The AI can be embedded into a CPU, becoming a coprocessor. Then you have to simulate it in a Gen5, right? It can be a standalone an AI accelerator or other, right? So you have to cope with different platforms using different tools.
So I have another question is about for beginner, right? How long will he or she to learn all these tools together and then to get familiar with them and then play them safely?
It's a teamwork, and I don't think one sole person can get into all these tools. I think everyone should focus on some part or some layers or between some layers, depending on that.
Okay, thank you. And the Miss Song Yang, because I see you have very interesting background, so we're very curious which kind of design tools you use, because I know that you will launch the first rocket of urban space next year.
Yeah, hi everyone. I was doing DeFi, designing AI chip since 2016 to 2018, and it was acquired by Xilinx, and now I'm starting a new startup working on commercial rockets. So for now, you can see rockets design is quite different compared with designing a chip. So it's a complex system engineering. We used to use a lot of design EDA tools like Cadence ones, Synopsys ones, and we were using PyTorch, Caffe, MXNet, and we were also doing our own compiler, and now it's called Vitis AI. But for now, since our team is designing our commercial rocket, so it's quite different. So we are using aerodynamics, kinetics, combustion simulation tools like Fluent, and we are also using some PCB board designing tools like National Instruments ones. We are now we have not using AI algorithms onto our rocket design and rocket control. So we are not using such frameworks like Caffe or PyTorch on our design. So it's quite different compared with designing a chip. So we are using so many things for combustion simulation and aerodynamics simulation and a lot of other things. Yeah.
Okay, thank you. And let's move forward to the next question. Given your experience in the embedded systems, because here the four panelists are all experts in the embedded system domain, and I think most of them have the experience in industry, or some experience in collaborating with industry partners. So we just want to know what is the biggest difference in the way people from academia and the industry look and care about design automation. Okay, Professor Jie Liu.
That's an interesting question. Being in the industry for many years and now in academia, I think I heard some saying that I want to recite or try to recapture. In industry, you try to do the best things, and in academia, you try to do the right things. I think that's the difference. In industry, for any tools or any products you do, you chase for performance, you chase for ease of use, you chase for commercial success in the end. But on that way, right, you use the most mature technologies. You try to adapt to people's design habits and use cases, you do any shortcuts you can, right, to get to in that version the best product you can. In academia, at least I think what should be happening is you think through the whole picture, and you try to find what's the right way of, quote unquote, right way of doing it. And the most successful ones are the ones really from the ground up think about the foundations, the concepts, the rationale behind the tools, and you try to prove, right, a whole train of thoughts and how that connect together and become a whole story. And in academia, you don't have the engineering resources or the experience to do the whole sort of user experience, the whole flow for the commercial success, and rather you try to hit the nail on the head and solve a particular problem, but solve it in the right way. So that's I think to me, those are the differences between commercial tools and academic, I would call them exercises. And even for the most successful ones, the most, I would think when I was at Berkeley, we do quite a, the Ptolemy software we did was quite close to a commercial tool. But now by looking back, it's very far from being a commercial software. So I think that's the biggest difference.
Okay, thank you. Because we know that a lot of companies they want to make the workflow of their the products in an engineering way. So most of them are developing their own tools to make their products to be more efficiently developed. So I think that do you think that the design automation tool in this way can help them to improve their their productivity and the product performance. And Professor Liu.
I'm sorry, I didn't hear you very well. I'm on the car on the road.
I mean that do the design automation tools can really improve the productivity of the companies and help them to optimize their develop teams, or can help them to increase their profit?
No, I think you can. The strength of being in academia is you can try many ideas and you can fail fast. You know which one works, which one doesn't, without too much of a bag of whether or the commercial upside or downside. And with that, right, you can try to test a lot of ideas and try to find the one. But on the other hand, I don't expect academia to have the resources, the engineering resources to go the whole 9 yards to go all the way to commercial success. But on the other hand, and that's where the R&D departments in the industry should do. They should connect to the academic ideas and toy examples or those toy tools, and then try to bring the best ideas and components that those are proven to be successful, and bring them into the products and to improve the products. In some way, most of the EDA tools we see today have their roots in academia, but after they become commercial tools, they went a long way they go much more beyond just what's embraced or embedded in the academic thoughts.
Okay, thank you. Oh, okay, Professor Zhang, can you share your can you give some comments?
Yeah, I agree with Professor Jian. Actually, you see that for the collaboration between academia and the industry, the difficult part is that whether we can find the common interest. Actually, for academia person, particularly like me, a theorist, we are more keen on you see that the theoretical challenging of the problem. Particularly, we are trying to work out some of the novel solutions to the problem. But for the industry person, they more keen about the practical problems. They don't care about the solutions is novel or not. They need the solution should be effective and easy and efficient. For example, for some experience from my side is that, for example, for my collaboration with the Chinese Space Center, you see that they have lots of practical problems, but many of these problems can be solved using some existing technique, which are not so challenging. So, but they are real problems for the industry person. So they hope that we can provide some of the technical support, but that could be not so interesting for academia person. But so it's really challenging for the collaboration. You need to find the common interest. For example, maybe actually you see that for the collaboration, it's not easy to find some of the challenging problems for academia person, but they are still useful for the industry. So for example, for our cooperation with the Chinese Space Center, you see that for in the past decades, we did find some common interest. For example, for some of the safety critical software verification, particularly, for example, for the Chang'e 3, for the hardest part is the soft. It's called the soft landing, means that the lander using some of the company control procedure landed on the surface of the lunar. That procedure is really difficult. So we found the common interest. Yeah. Okay, that's it. That's my point.
Okay, thank you. And okay, I quite agree with the previous two analysts. I think the first one is like Professor Liu said, academia try to do the right thing. Normally they will have a problem, right? To formulate a problem, to solve it, to show the innovation. By doing this, they can, academia can make a lot of assumptions about their conditions or how to use it or all different aspects. But in industry, any of these assumptions will probably make the tool fail because there are a lot of different departments. Like some care about performance, some care about the power consumption, or some are concerned about the new tools or the new techniques. It's not friendly to the massive number of developers because not all developers have a very good background on the system. Right? Some only familiar with the programming software part, but not the system. System engineering is a very few part in the whole group of R&D persons. So I think this is the first difference. The second one is I think like Professor the second panelist mentioned. There are lots of challenges actually because I'm also in Huawei, and Huawei have announced a lot of technical challenges, right? To a lot of university, you can see that. And according to the statistics, few of the research result can be directly applied to the problem, and most likely we'll see that. This professor, the work he has done is quite, you can learn it from it, but you cannot use it. So normally you will have a more, tightly coupled collaboration phase, right? Ask to form a project, to look into the detail, tell the professors all the important aspects you have to consider. Some of the assumption you should be eliminate it, consider it into your solutions, these kind of things. Yeah. So these are the major two differences.
Okay, Mr. Yao Song Yao.
Yeah, in my personal view, actually, I think in academia we look for the best performance in some core part. For example, how to shorten the time of compilation for 10%. And in industry, we care more about the full functionality. So I have two examples. The first example is actually for chip design, not for our design automation tools. For example, I believe there are some professors in our panel and our audience that are designing AI chip, designing the micro architecture. And but if we are doing a real chip that can be used by your customers, actually, apart from the core microarchitecture, you need to have your HDMI interface, VGA interface, codec, ISP, DDR controller, and a lot of things. And then your fully functionality SoC, and then your customer can use it. So only a core microarchitecture cannot be used as a product. Besides it, since I'm designing our commercial rocket, so I just mentioned we are doing aerodynamics simulation, kinetics simulation, thermodynamics simulation, and even combustion simulation. And all 4 simulations are in 4 different software tools. So it's quite annoying, actually. You cannot imagine that you are doing a simulation of a chip, but resistance simulation using cadence and the capacity simulation using synopsis. So it's very hard to design the chip using different software simulating different aspects. So we care, I think in industry we care doing all of things in just one software with fully functionality, so that will be a good product. So that's my personal view.
Okay, thank you. It seems that there are a lot of requirements or some expectations from the industry, the companies, and there are still a lot of challenges to be solved in the future. And some research questions can be abstracted from these problems, and the researchers can use this for their future study. Okay, and the next 2 questions will be moderated by Chenren.
Okay, yeah. So basically, Mingsong and I will take turn. And the third question is about the AI relevance. So today, AI is really hot and popular. It seems to penetrate many different domains and aspects in our daily life, including our research area. So the question is about what is the role of AI techniques in the system design and design automation of embedded or cyber-physical systems. I know Song Yao has an upcoming event to run, so maybe this time we will start from you. We will choose the reverse order.
Yeah, I think for now, actually, the aspects I just mentioned, actually, AI has not doing anything in this area. So we're exploring how to use, deep reinforcement learning for rocket control, how to use deep reinforcement learning for structure designing, and we also need to do some intelligent rocket design. For example, how to detect the maybe problems automatically and like that. So far, actually, as you can imagine that rocket design is a very high technology thing, but actually all these design automation tools and all these core technologies are, I think, 10 years old, even 20 years old. For example, we are using chips that maybe less performance compared with the Intel CPU 20 years ago. So I think there's so many things we can do in this area, and that's why I'm keen to attend this panel and eager to have more collaboration with our professors.
Cool. I'm hearing basically the technology is much more advanced than the existing domain, and there's a bright and optimistic, a very hopeful future in this area.
Yeah, I think there's so many things to do in the future. Yeah.
Cool. Okay, so Professor Li Jiang, we would like to hear your comments.
So yeah, actually, I have something to share here. I think in a complex system, especially in the cyber physics system, is very complex. So in this complex system, it's very, I think the AI in the future, AI will be very important. I want to share the information from the Turing awardee, Professor I think Joseph from Italia. He had proposed a system design methodology called autonomous system. It's not only a methodology. In his concept, in the future, the system should be autonomous. It can manage itself in all design aspects, including performance, reliability, and adaptivity to the different environments, interactions. And so in this autonomous system, AI will take a very key part. The AI should observe and will observe all the environmental and internal states, and it needs to do some decisions, make some decisions. And a small system is not enough, especially for the computing capability for such autonomous AIs. Therefore, all these kind of embedded systems should be connected to the brain somehow in the cloud or in the edge to form a very intelligent and autonomous system to face all the challenges here. And I want to advocate that now the majority or lots of the research resources are dragged into or only focus on those very hot topics like foundation models or these kind of things. But in embedded system, there's a lot of challenge, problems, including system design and AI algorithms, how to train the AI, incremental train the AI in the runtime. All these kind of techniques are, very challenged, and there's no big breakthrough in this domain.
Okay, thanks for your sharing. Professor Naijun.
Hi, Chen. Actually, you see, it's quite an interesting question. Actually, we have been considering this question a long time. Actually, you see that currently you see that for complex embedded or physical system, actually many of these systems contain AI components already. For example, self-driving and so on. So how to design this system actually is real challenging. This is my first point. The second point, you see that actually for design this AI based system, you see that there are lots of quite challenges. Firstly, how to modeling this system. For example, you see that actually many of this system are deployed in some open environment. So actually you see that the uncertainty and the unknowns of this environment. Also, you see that the interpretability And also you see that uncertainty of AI components give rise to difficulty to the design of this system. Particularly, you see that for these systems, normally this system is high dimensional, means that the state space quite complicated. How to guarantee the correctness of this system, particularly for safety critical systems of this system, is really challenging for the traditional theories. For example, traditional verification technique mainly based on symbolic computation. You see that. So actually, that's really a problem. How to extend this classical verification technique to deal with this AI-based systems. Currently, you see that there are some trends. For example, maybe we need to use some of the pack correctness, pack sense correctness. So that you see some in recent years, there are lots of techniques proposed by combining classical verification technique with AI-based technique together for guarantee the reliability of this system. Finally, you see that for this complex embedded and separable physical system, so adaptability and self-evolution also are very challenging problem. I think maybe AI-based technique could be a solution to the challenges. So that's my personal perspective. Okay, Chenren.
Okay, thanks, Professor Chen. Okay, so Professor Jie Liu, so I know you recently have been working on AIoT, and you are the founder of the embedded AI conference, and also you have a lot of experience in applying AI and IoT technology in the smart agriculture. So maybe can you share some of your recent experience?
Yeah, to me, AI is very much a methodology and a way of thinking these days. As a methodology, let's just narrow down to what we currently refer or commonly refer to AI these days, right? In fact, AI should be a much broader sense than deep neural networks or these training-based methodology. But let's just narrow down on that. I think what AI can do for system design could be on several parts. For one is to handle very complex problems. Most of the design problems are fairly, design optimization problems are fairly complex, and most of the interesting problems in there are NP hard. And AI is a way of tackling those problems using data-driven, using things like GAN, things like synthesizing data to train a model and try to optimize it to close that loop. Because most of the design problems, you have a very well-defined formulation of what optimal is. So that's a very natural way of formulating those things into a AI problem. In fact, I think Google did a very good job on using AI to do layout optimization and published a paper in Nature. One of my interns in the past were on that team. I think it's a very interesting work. So that's one, using data-driven and optimization to solve design problems. The other trend I see, or I can see that's interesting, is because of the way that people invest so much into AI, like the computing platforms, like the backward propagation and optimization to nonlinear optimization tools and so forth, those hardware and software and optimization methods can apply to design automation problems. If you can formulate a problem into a sort of a backward propagation or even a network of quote unquote decision making nodes, and you can formulate it into a sort of AI training problem. Then you gain a lot of hardware and software accelerations or accelerators that can help you to optimize those things much better. And we've seen also in design automation communities, people are doing that. And I think one of the best papers a couple of years ago from that was particularly on those type of approaches. And the beyond those two, I think AI can also bring a lot of challenges, just because many systems we're dealing these days, especially with AI as a components in there, we can't tell, or it's very hard to say precisely where the boundaries of the optimalities are, and most of the outcomes of these AI-based systems are stochastic. We can only say in general, or with what kind of probability this thing will perform in the right way or in a close to optimal way. And for many cases, those are fine. But for other cases, determinism, like proven to be correct and so on, it's very challenging to deal with those kind of AI problems. Yeah, I know my signals may not be very good, so I hope I convey the message.
Yeah, I think we can hear you well. Thanks for your sharing.
Actually, Chen, I actually have a question to Professor Liu. It's a very interesting that Professor Liu has mentioned that using AI to solve the optimization problem. Actually, this is what I am currently one of the problems I'm looking into in Huawei. Actually, in the computer, in a very complex system design, you have lots of design. When we do design exploration, you have a lot of optimizing space, like in the layer of software, in the layer of to have a compiler, right? How to optimize the instructions, how to fuse the operations, this kind of thing. So you have a domain here, then you have a domain in, for example, microarchitecture. You have another optimization domain in the, for example, system on the chip. And these all these domains, actually you can use AI to behave like a solver to solve the optimization problem. But in a very complex system, these domains are coupled with each other. It's more like the solver behind the solver, beyond the solver, beyond the solver. So it's a several MD-hard problem coupled with together. So how to deal with that?
I don't think I have a silver bullet, but in many of the just in neural network in particular, let's say there's the neural architecture search like problems, precisely like what you described, right? They have an inner loop, which is already a very hard optimization problem, and then they have an outer loop that would change meta parameters or the structure of the problem, and then you could embed those kind of things on and on. People are using various ways like reinforcement learning, like genetic algorithms and so forth. It really becomes I hope you won't sort of do it in a brute force way. You try to optimize the inner loop, and then that's a set of parameters you optimize from the outer loop and do it on and on. If there's a way of quickly predicting what works and not, where those kind of things, I think some of the AI tools can help. AI are good at predictions. If you can do an early exit, right? If such approach doesn't give you promising direction, and then you change your optimization directions and so on. Those kind of thoughts or methodology, I think may help in here.
Okay, thank you.
Okay, then comes to the last questions. The last question is about the forecasting. We would like our panelists to predict the future. So basically, where are the real opportunities and challenges for embedded system design automation and their cross term. The cross term is really the focus of this workshop. So this time we still start by Professor Li Jiang.
I think for these two domains and the cluster, I think AI will be the opportunity, as I just mentioned in the last question, because design automation, AI technology is replace or partially replace some of the heuristics proposed by human beings and play a more important role in design automation. And on the other side, in the embedded system, I think I also have mentioned that AI will become a key role in the future very complex autonomous systems. I think some of the leaders in Huawei have also proposed an AI native system. Everything is originated or considered through by AI. For example, we have lots of algorithms, applications, algorithms in applications or algorithms in the systems like scheduling or this kind of algorithm can be think again using different perspective in terms of AI. So I think AI will be, in my mind, AI will be a true, opportunities for these two domains and their cross section.
Okay, thanks, Professor Li Jiang. Professor Naiji.
Hi, Chen. For the embedded system design and the design automation and the cross term, personally, I think maybe we can consider from the following aspects. From the embedded system design to the design automation, I think maybe there are the following two opportunities. The first one is, for example, for the design complex embedded system. Currently, I think maybe there could be the trend to combine data-driven design and the model-based design. For this combination, I guess the design automation is definitely necessary technique. Also, you see that for the model-based design and actually you see data-driven is widely used to build the model for the design. So once we have the design, definitely we need to use the model-based design. For the model-based design, we need to consider the model transformation among different abstraction layers. So that you see that particularly, I guess that the model transformation needs some of the design automation technique. So I see the two opportunities for the design of embedded system needs the design automation. For the inverse direction, I also see the two opportunities. Means that the first opportunity is that for the embedded system design, particularly for some safety critical systems, definitely we need lots of automatic verification and monitoring technique. I guess this technique are useful for the design automation. Actually, I think most of this technique themselves are design automation technique already. Okay. Also, you see that for design embedded system, we need a modeling technique and also some specification technique. Certainly, these technique are necessary technique for design automation. So That's my personal perspective. Okay.
Thanks, Najee. Jie?
Yeah, I think in my view, most of the interesting problems we are going to build in the future will be embedded systems or cyber physical systems that has both the electronic or intelligence part and some kind of physical systems that interact with the world, in particular, open complex world. And from what I see from the EDA side, we don't have enough tools to deal with this challenge. That's for one. The other is we haven't done a very good job of educating designers or system builders. Many of them may not be trained as a system designer to use these tools. People tend to still follow a very traditional way of building and writing code and do the compiling and test it without much of a methodology to guide what to do. And I think that itself is a big challenge. And to do sort of move forward with that, I think for one, we want to know the best practice and best cases, the use cases that will educate and let people know how to do quote unquote the right things. And the other is with coming up with tools that are more friendly to various domains. These days, most of the tools we have probably are focused on EDAs and design sort of electronics. But in fact, we have many different kinds of systems that in big need of good design tools. And we also need to educate people to know the practice and to benefit from those tools. I think that's where the two communities should come together. One from the system side and one from the tool side, to go hand in hand and to form maybe some benchmark problems with the high visibility on both sides to better form this community and to with the best practice, the quality driven or the correctness driven best practice to improve how we do system design and build better systems. And that's my view.
All right, thanks, Jie. Now I'm handed over back to Mingsong.
Okay, I totally agree with the panelists, their view about the challenges and opportunities for the data automation in embedded systems. So now, due to the time limit, we can have one or two questions from the audience, online or offline. Any questions?
I have a question. So thanks for all the panelists for the great insights. I have a quick question. So given that I think the design automation techniques were very successful in chip design because it's a huge sector, right? Semiconductor design. And the problem is more or less eventually formalize a very clearly defined mathematical problems, a set of problems, of course. Now, in embedded systems, especially with so many different sectors, right? They all vary quite a bit from each other. From design tools perspective, should a tool developer try to develop some general tools that can be applied to multiple domains, or they should focus on one or two particular domains? And if so, which domains are the most promising ones?
Okay, who can answer this question? Steve?
Hi, Chi. I think maybe I can answer Chi's question.
Yeah, Professor Najin.
Yeah, because I'm working on the problem. Actually, you see, currently you see that certainly for some of the specific specs, particularly for some of the spec domain, definitely we need some of the spec tools to handle the spec problems. But for the whole system, we need to integrate these tools together. So that is indeed challenging, how to integrate these tools together. For example, the difficult part, for example, maybe we need to build the common semantics so that these tools can be integrated, interact each other. The other issue, I think, maybe as you mentioned, you see that once we put all these design features together, you see that the system will become quite complicated. Actually, for the hardware design, you see that design automation techniques are very successful, because you see that for the hardware, so the design space is still finite. So definitely we can find some very efficient design algorithm for the problem. For the system design, particularly, you see that many you see that the state space is infinite, even more. So for this design space, you see that it's really hard for finding some of the design automation technique. So currently, I think maybe we possibly you see that maybe we relax the exact correctness to some of the quantitative correctness. That could be a solution, but I'm not so sure. Yeah.
Okay, I can add some of my points. Actually, the difference between the embedded system and the chip design is that for the embedded system is there are too many layers of design abstractions, and the variety is too large, like Professor Chen has just mentioned. So I think there are two things in my mind currently that I think is very important to design automation tools in embedded system. The first one is we need to define some standard like benchmark. Although you have different domains, but in each domain or some of the common parts, you can define some benchmarks so that different groups of design automation tool developers can have a single target or have a similar target, like in EDA tools. In different phase, we can choose different tools from different companies, but they are doing the same thing. They have the same benchmark, right? I think the second one is because there are too much variety, there are too much stages. These tools have to be have good interface so that different tools can be integrated easier from single tool to tool chains. I think these are the two points are in my mind.
Okay, Professor Liu. Hi, Professor Jie Liu.
I would say domains. I would think what do you call it? Mechatronics, right? Those are the mechanical systems and electronic systems together. I think automotive is a big industry that needs a lot of design tools, and design tools will help. Robotics is another one. I think those are the places I would look for commercial success for embedded system design tools that will learn from or borrow ideas from EDA, from electronic design tools into new domains. I think, in fact, there are some, but not as much as what the success of the EDA tools. That could be.
Okay, thank you for the panelists. And now I think we because of the time limit, we cannot have more the questions from the audience. Okay. Finally, we will end the panel. And firstly, I want to thank to the panelists for their sharing and based on their very strong experience. And we also thanks the audience online and offline to participate this this panel. So Chenren, do you have some words?
Oh, I don't have any. I don't have too much to add. I think Mingsong and me are very grateful to all the speakers, panelists for your great sharing, and also the participants for your support. We hope to see. We will have more upcoming events in the cross-SIG format, and hope to see you soon in the future, especially offline, in person.
Okay, thank you. Okay, see you.
See you.
Oh, shall we actually all take turn on our camera and take a
Okay, yeah. But I think the sound has left.
if possible. If
Let me try. I can't see myself.
Okay, we need to close the. 停止是。会自共享吗？这东西。Okay. Yeah. Maybe we'll see here. We'll start. Okay, so every people, please open your camera. We can take a picture together. Yeah. Okay. So Chenren, can you capture the picture for us?
Yeah, sure.
Okay.
Jingyu, let us know once you finish.
Yeah.
Have you finished?
Yeah, just one more second. Okay, yeah, we're finished.
One more.
Okay, let's do one more. Okay, done.
Right.
Okay, thanks speakers and the panelists. Bye.
Thank you, everybody.